In the next few videos, I want to go through an example of applying some steps for conducting mechanical analysis of a movement. And I'm going to do so using this little checklist guide here. There's an expanded version of this available on the Canvas site, which has some details for each of these steps, which hopefully I'll be able to explain as we go through this. And I want to go through this with an example of a particular piece of equipment that I've worked with in the past, which is this Ultra G anti-gravity treadmill. So if you haven't seen these before, it is a regular treadmill, but it has this chamber here. And you zip yourself into it with this rubber skirt thing. And how it works is the chamber is pressurized, meaning the air pressure inside here is higher than outside. And as a consequence, that air pressure pushes up on you, and it reduces your effective body weight. Now, it doesn't actually, despite the name, it doesn't actually reduce gravity, but what it does do is it provides an upward force on your body that counteracts the force of gravity. So I think this will be a good example to go through to talk about how you might be able to use this in a sports performance or rehabilitation situation. And hopefully you'll find this type of analysis we're doing useful for when you're doing your equipment analysis, and as also for exam 4. When I was coaching high school cross country, the team I worked with had one of these, and we used it to a lot of success with athletes who were either injured or on the verge of injury to reduce the loading induced by training to an amount that was tolerable for whatever their mechanical condition was. So the first thing to do here is ask, what question am I trying to answer? So suppose somebody had maybe, I don't know, patellar tendinopathy. Their patellar tendon was injured. So the patellar tendon, of course, is right here, and it's connected to the quadricep muscles. So we might be interested in how much force is required from the quadricep muscles, and maybe how can this treadmill, or will this treadmill, reduce the amount of force required by the quadriceps? So that's our key question that we want to answer. The next thing we can do is we can dive into starting to analyze this and starting to formulate a little bit of a simplified model of this system, this runner. So as I'm explaining this, I'm drawing up a little model. I've got a torso here. I'm going to put in a femur and a hip joint, or and a knee joint, and a leg. Now, because we're only interested in the quadriceps, and the quadriceps are acting primarily about the knee joint, maybe we can just ignore the foot and ankle completely. Maybe we can just not include them. Seems, in this case, seems reasonable to do. Of course, if you were interested in something else, like forces in the Achilles tendon, maybe that would not be such a reasonable thing to do. So number 2, let's think about the external forces. I already talked about one of them. One of them is the upward force from the anti-gravity treadmill. I drew it up here just to get it out of the way, but you could think about that as the net effect of all the air molecules in here pushing up like this. So that's one external force. Another external force that you will see in almost everything is the force of gravity acting on your body's center mass. So the force of gravity is going to be pulling down like this. So those are the 2 major external forces that we're going to be interested in. Then we might ask, what joint or joints are involved in the exercise? Now, of course, that's just going to be the knee joint right here. But sometimes you might be in situations where you're interested in multiple joints. So in squatting, for example, you might be interested in simultaneously the hip joint and the knee joint. The next thing we should think about is, what are the internal muscle forces involved in this motion? So if we're specifically interested in what's happening at the knee joint when you're running, the muscles we might care about would be the quadriceps, maybe the hamstrings, maybe the gastrocs, because they also cross the knee joint. But because we're trying to simplify things here to understand them better, maybe we can make a few relatively simple assumptions. One of them, maybe we just really are interested in the quads, and we can assume the hamstrings maybe aren't producing that much force, or maybe they're producing a little bit of force, but not that much. And likewise the gastrocs, maybe they're producing some force like that. But really what we're interested in is the quadriceps, and not even the action of each individual, like the vastus lateralis, medialis, et cetera, but maybe we could just imagine them as one big muscle. And what they're going to do is they're going to create a muscle force that acts on the tibia, kind of, and goes on a path like this, that will have the tendency to extend the knee joint. And that's going to work to overcome, and we're getting ahead of ourselves a little bit here, but to overcome the tendency of your body weight to flex your knee joint. So for this very simple analysis, we're just gonna care about the one big lumped quadricep muscle. Then for number 5, we can think about what joint torques do the external forces create. So that would be this force, this force. So what kind of torque are they going to create? Well, a torque is the force times the moment arm. So what's the moment arm of this force? Well, it's going to be, want a line of action, and then it's going to be that distance. And what's the moment arm of this force? Well, it's going to be, again, I want some line of action for the force, and then it'll be that distance. Oops, that perpendicular distance. Now, something interesting here. Notice how the upward force here is going to have a tendency to counteract the downward force here. So we could think about this in two ways, One of them is that this force creates a knee extension torque, whereas this force creates a knee flexion torque. Maybe a more simple way to think about it is to just add these two together, and if you'll allow me to just redraw the green arrow as the net effect of the downward force of gravity minus the upward force of the alter G lifting you up. So you would get some net force, like, maybe I'll draw it like this, with just the reminder that that equals gravity going down plus the treadmill lifting you up. That gives us that right there, that net force. Now it's still going to be down, because maybe you dialed this thing in to run at 80% of your body weight. So it's going to provide an upward force of 20% of whatever your weight is. So the net result will be you'll be weighted down at 80% of your body weight. And we'll just draw that as that green arrow right there. So we've simplified this external force into just one force like this. Notice how it's fairly clear that this force is going to have the tendency to flex your knee, or it's going to have the tendency to create a force or create a torque via this moment arm that tries to bend the knee more. Because imagine if you just completely relaxed your muscles and you were running, your knee would collapse and you would fall into the ground, right? So there's going to be a knee, and maybe I'll even write flex, knee flexion torque from that downward force, that external force. And we could think about, what are the joint torques that the muscles create? Well, it's going to be whatever this red force is multiplied by whatever the moment arm of the muscle is, which maybe it's kind of hard to see exactly which direction it'll be going, but it'll be something like that distance. So that's small-ish distance. The exact number isn't super important. What is important is that distance is quite small compared to that distance. So immediately we can probably guess that the force of the quadriceps here is going to be much, much, much bigger than what this force is, which is 80% of your body weight, we said. So that force is going to have a tendency to extend the knee joint. Now that should be pretty clear, because if you've done any kind of structural kinesiology or anatomy, you know that that's what the knee extensors, the quadriceps, that's what they do. So we'll write maybe extend. extension torque. And the amount of that torque will be equal to whatever this muscle force is here, multiplied by whatever that moment arm is. So that's the net effects of our external forces and the muscle forces. And we've considered the forces, the moment arms, and the torques they generate. And the whole, the balance of those torques, meaning this knee extension torque compared to this knee flexion torque, is going to determine what happens when you run. So if you're trying to push yourself off the ground, meaning you're trying to have straighten your knee, push yourself up, this torque needs to be bigger than that torque. And this is something that I think is also demonstrated in the problem set 4. If you want to extend a joint, you need to have the extension torque bigger than the flexion torque. So since we're halfway through here, maybe I'll make another video where we start talking about the specific muscle properties that might go into what's going on in this situation.